Well, today we will be talking about three-phase induction motor. So, an electric motor is an electromechanical device that converts electrical energy into mechanical energy. In this case, three-phase AC operation, the most widely used motor is a three-phase induction motor, which is a type of motor that does not require an additional starting device. This type of motors are known as self-starting induction motors. A three-phase induction motor consists of two major parts, a stator and a rotor. So this is the construction of three-phase motor that we can see. One of the construction of a motor is a stator. The stator is made up of a number of stampings in which different slots are cut to receive three-phase winding circuit which is connected to three-phase AC supply. The rotor consists of cylindrical laminated core with parallel slots that carry conductor bars. Conductors are heavy copper or aluminum bars which fit in each slot. These conductors are braced to the short circuiting end rings. The frame is the outer body of the motor. The function is to support the stator core and to protect the inner parts of the machine. For smaller machine, the outer frame is casted, but for larger machine, it is fabricated. And the next one is the motor shaft. Shaft is the mechanical component for transmitting torque and rotation. So here are the types of three-phase double cage rotor motors. The simple squirrel cage induction motor is superior to slip ring induction motor on account of motor output, frame size, initial maintenance and repair costs. Next one is the three-phase synchronous motors. The synchronous motor is a constant speed motor whose speed is fixed by the supply frequency and number of poles, and therefore is independent of load. Since this motor is not self-starting, therefore some special arrangement is required to be made for making it self-starting. Synchronous induction motors. The synchronous induction motor, as its name implies, is a machine which is capable of running both as an induction motor and as an asynchronous motor. The next one is variable speed commutator type 3-phase induction motor. This is also an improvement of the plain induction motor designed to provide a variable speed. It also consists of a commutator winding placed on the rotor in addition to primary winding, whose EMF is collected and injected into the secondary winding placed on the stator. The next type of motor is decompensated induction motor. The motor is an improvement of the plain induction motor designed to operate at approximately unity or slightly leading power factor over the whole range of loads. The next type of motor is the three-phase AC shunt commutator motor. In this motor, the stator is connected directly to the supply while the motor brushes are connected to the supply through a transformer.
Explain the principle of operation of a three-phase induction motor. We know that when a three-phase supply consisting of three phases and a neutral wire is connected to a three-phase induction motor, its rotor starts rotating. Let's understand what makes the rotor rotate. When a three-phase AC supply is connected to the three-phase stator field windings, they start behaving like electromagnets and produce three independent alternating magnetic fluxes. The resultant of these fluxes is called the net flux. We see that its magnitude remains constant, but position keeps on changing with time in circular manner. Hence, net flux develops a rotating magnetic field in the stator, which causes relative motion between the net flux and the rotor. Since the magnetic flux linked with the rotor keeps on changing, a current starts flowing in the rotor winding. As per the Faraday's law of electromagnetic induction, the direction of this current is given by the Fleming's right-hand rule. We know that when a current-carrying conductor is placed in a magnetic field, it experiences a force. Similarly, when a current-carrying rotor is placed in the stator magnetic field, it experiences a force and starts rotating. The direction of rotation of the rotor is the same as that of the rotating magnetic field of the stator.
To reverse a three-phase motor, you just swap any two power leads and the motor will run in the opposite direction. To reverse a three-phase motor using contactors, you just run one set of wires straight through one contactor and a parallel set of wires through another contactor where you swap one set of wires. When this contactor is engaged, the motor turns one way, and when this contactor is engaged, it rotates the other direction. You can swap either the line or the load wires, not both of course, but most folks seem to like to swap the wires on the load side of the contactor to keep things clean and consistent. Well, that looks simple enough, but there's a problem. What happens if you accidentally engage both contactors? Well, now you're shorting out two of the three phases of your power system, and that usually makes bad things happen.
Speed of three-phase induction motor can be controlled from both stator and rotor side. So first we discuss the speed control from stator side. So these are the three methods. Number one is frequency control or V by F control method. Number two is stator voltage control method, and number three pole changing method. These are the main methods of speed control from stator side. So now we are discussing one by one. So first, frequency control or V by F control method. The torque and speed of induction motor can be controlled by changing the supply frequency but keeping the voltage constant. If frequencies decrease keeping voltage constant, then saturation of air gap flux takes place. So at low frequency or low resistance, the current may be too high. So it is important to maintain the flux phi constant, and it is only possible if we change the frequency at the same time if we change the voltage also. So it causing the no change in flux, and if the flux is no change, so there is no saturation occur. So hence it is remain constant. So we are keeping the V by F ratio as constant. That's why this method is also called V by F method. So that is how we control the speed of three-phase induction motor by this method. Next is stator voltage control. Stator voltage control is a method used to control the speed of an induction motor. The speed of an induction motor can be varied by varying the supply voltage, as we seen from the equation that T varies to S E2 square R2 divided by R2 square plus X S2 square. As we already seen from the equation that we know that the torque developed in the rotor is proportional to the square of the supply voltage, and a reduction in stator voltage will produce a reduction in speed. So therefore the continuous speed control may be obtained by adjustment of the stator voltage without any change in stator frequency. So this method gives a speed control only below the normal rated speed by reducing the voltage. This method is mainly used in low power applications such as fans, blowers, centrifugal pump, etc. Third method is pole changing method. In this method, as we know from the formula of synchronous speed, ns equal to 120 a divided by p, so it shows that the synchronous speed of a motor is inversely proportional to the number of pole of the stator winding. So by changing the number of pole, we can easily control the speed of a 3-phase induction motor. So the number of stator pole can be changed by 3 methods. There are known as number 1 multiple stator winding, number 2 consequent pole, and number 3 pole amplitude modulation or PAM methods. Now coming to the speed control from rotor side. In rotor side there are 2 main methods of speed control. Number 1 is adding external resistance on rotor circuit, and number 2 injecting EMF into rotor circuit. Adding external resistance on rotor circuit method. This method is used in slip ring or wound type of induction motor. In this method, the speed of an wound induction motor can be controlled by controlling an external resistance in the rotor circuit through slip rings. If the resistance of the motor increases, then the pull-out speed of the motor decreases, but the maximum torque remains constant. So in this method is not applicable in squirrel cage type induction motor. It is only applicable for slip ring induction or wound type induction motor. And the last method is injecting EMF into rotor circuit. In this method of speed control, external voltages add into the rotor circuit of the motor and the frequency must be same as slip frequency. So injecting EMF is opposite in phase of the motor. It increases the rotor resistance. By that, this method can use to controlling the speed of induction motor.
As I told that these are the most widely used machine in the industries and they have enormous applications. To name a few, I have mentioned here the few applications. Like for example, they are used in electric train engines. To drive the engines in the electric train, we use 3-phase induction motor. Similarly, they can also be used for cooling fans that are used to cool large machines. So as you can see here the cooling fans are being used in case of a transformer, and these cooling fans are being run with the help of 3-phase induction motor. There is another application there. They are used in chimneys at the power plants, and we know the function of chimneys. They are basically to exhaust or to remove the unwanted or poisonous gases and fumes from the power plants, and that is being also done with the help of induction motor. A very familiar application is in the case of printing machines. So here also the printing machines are being run with the help of 3-phase induction motor. As well as they are used in rolling mills. They can also be used for large capacity exhaust fans. Now you can see here, these are the exhaust fans which is generally being used in industries to remove the unwanted gases, and here also induction motors are used. Then this you might have seen the cranes which are being used to lift equipments, and here also these cranes are being operated with the help of 3-phase induction motor. Hoists, this we generally see near the construction areas, and these are also being operated by the 3-phase induction motor. A very common example is the lifts or the elevators, which we often come across in apartments, in malls, and in many other places. So they are also being operated or run through the 3-phase induction motors. So these are few applications which I have mentioned, but there are other n number of applications of 3-phase induction motor. Now, since I'm telling that the application
common failure types, well, this is close to the breakdown of where failures occur. On most motors, you're going to have about 50% attributable to bearing failures. You're going to have about 16. This is argumentative. You can say 16 to 20. You might say 45 to 55. But this is relatively accurate. External conditions, about 16%. some of the things we've talked about. Unknown, there's an unknown category where you can't figure it out, about 10. Rotor bar is somewhere in the 5 to maybe 7, just depending on the application, percent range, and shaft and coupling. Induction motors will operate under the most adverse conditions, and they'll keep trying to operate, but those conditions are usually preventable. And unfortunately, the fact that they're preventable, the problems that occur from human abuse, operators that don't understand, or maintenance people that, and I'm not cutting down on maintenance people, but maybe they don't understand the impact they're having on the motor when they excessively start it, or they just do different things that they don't realize that they're causing damage. That's where education comes in. Most bearing failures can be prevented. They under lubrication or over lubrication. There are so many conditions like that we see almost every day, but it can be prevented by teaching people not to put too much grease in or not putting enough grease in. Additional causes could be coupling misalignment, soft foot conditions, mixing incompatible greases, applications with variable frequency drives and not taking care of the circulating currents that are generated by the drive. There are ways to handle that, just different things like that. Example of an under lubricated machine or motor, you can see how hot and how dry it is. Believe it or not, we see this not every day, but very commonly still, condition where we have over lubrication. That guy was really good at lubricating, but he lubricated so much that he caused damage in the other direction. Wiped sleeve bearing, just showing an example of a sleeve bearing and the failure of that bearing. Can be caused from contamination in the oil. A number of things can cause that. Broken shaft, in this case, excessive belt tension on both of these causing the roller bearing to fail. Roller bearing fails, generates all that heat, and then causes the heat in the shaft, and then the shaft breaks. This is an example of just losing a bearing and then the rotor touching off on the stator. In this example, we've got aluminum that transfer from the rotor to the stator. Not uncommon, not always a complete disaster. You can typically, believe it or not, clean that up, and or if it's a rewind, you rewind it, do a core test, clean that iron up. It just depends on the magnitude of the failure. The rotor, on the other hand, depending on how bad the damage is, you might have to replace the rotor, or from my perspective, convert it to a copper alloy. Mechanical overload. So winding failures contribute 16 to 20%, and the leading cause is overload. The windings fail because motors get pushed harder and harder, and people see that service factor and they want to push that motor into that service factor, and they think they're okay, but they're creating more heat, and that heat then fails the winding prematurely. Again, service factor is for intermittent, short duty. It's not for continuous. We do have the opportunity sometimes to take a design like this and get it in, and if it's a rewind, we might be able to increase the copper cross-sectional area. We might be able to increase the class of insulation, let's say from F to H, and actually allow you now to run without redesigning it at higher horsepower and get the same original life. But those are the things you look at and you work with your customer to determine, is this something you need in that application if you're going to continually put it in an overload condition? Or is it time to get a new motor that's rated better for the application? Oops, sorry. Starting and stopping, don't want to really go past that. That's a tremendously stressful time on the motor. And amazingly, we will have failures that a motor will fail or trip, and the operator doesn't get with maintenance, and he immediately turns it back on. And then they do it again, and they could do it 5, 6, 7 times. They finally get maintenance, this thing won't run. Well, they just now caused severe damage by hitting it over and over, causing tremendous heat. That can be prevented, and the extent of damage can be greatly prevented by teaching the operator to investigate why it tripped. Don't just automatically hit the button. It's human nature to hit the button, but that isn't necessarily the best answer. Thermal damage on the left here, just the picture showing just an overheated winding, and then a typical grounded winding at the coil at the edge of the slot. The reason that happens, and it's very consistently happens on grounds, is the coils are designed in such a way that the coil exits the slot and then that diamond shape. Well, blocking and bracing helps, but when you start a motor, you have that high inrush current, that winding wants to move. It wants to torque, it physically tries to move, and it will move if it isn't blocked and braced properly. So why you see a failure here consistently is because that's a fulcrum point. That's a point where the coil is being pulled, and maybe eventually it causes a failure in the ground wall. Rotors account for 5 to 8%. The failure on the left is showing a bar that's lifting, broke from the shorting ring. Cracked shorting ring on the right, almost through the whole rotor. Again, typically only because of excessive starting and stopping. Bar ring to crack failure, and then a bar that's actually lifted. You'd be amazed at the number of motors that operate with bars that are lifted and they're dragging on the stator and they're operating that way. And the motor hasn't failed. Somebody hears something funny or vibration analysis picks it up, and then the motor's eventually shut down. And they're lucky, because typically that condition will cause a catastrophic failure. Conditions where the motor is externally or internally plugged and it's not allowing it to cool, too much contamination. A paper mill, obviously on this side, totally closed fan-cooled motor, but you took away the cooling mechanism. The cooling fan underneath this housing is designed to blow air across those ribs. Can't do it in this design. It's completely insulated the motor from being able to do that, so the motor's going to get hot and fail. Same thing on the left, but internal contamination.